For centuries, humanity has sought wealth in Earth's deepest veins, from gold to diamonds. But what if the next great frontier for resources isn't beneath our feet, but billions of miles away? What if a single celestial body held enough platinum to crash global markets, or enough water to fuel an entire space economy? This isn't science fiction. This is the trillion-dollar asteroid, the focal point of an escalating engineering and economic race that promises to redefine wealth and power. The stakes are monumental, the challenges unprecedented, and the potential rewards unimaginable, as nations and startups eye these cosmic treasure troves. On Earth, essential elements like platinum group metals and rare earth elements are finite and geographically concentrated. The United States Geological Survey, or USGS, consistently highlights the increasing scarcity and geopolitical sensitivity surrounding these critical materials. Platinum, vital for catalytic converters and medical devices, is predominantly sourced from South Africa. Rare earth elements, indispensable for everything from smartphones to electric vehicles, are largely controlled by a single nation, as reported by the U.S. Department of Energy. This terrestrial concentration creates supply chain vulnerabilities and significant economic pressures, fueling the search for alternative sources far beyond Earth's surface. Our solar system is teeming with asteroids, categorized broadly into C-type, S-type, and M-type, each with distinct compositions. C-type, or carbonaceous asteroids, are rich in water and organic compounds. S-type, or stony asteroids, contain silicates and some metals. But it's the M-type, or metallic asteroids, that truly excite prospectors, as they are believed to be the cores of shattered protoplanets, virtually solid nickel iron, often infused with lucrative platinum group metals. According to planetary scientists at NASA's Jet Propulsion Laboratory, identifying and characterizing these types is the critical first step in turning cosmic rock into tangible wealth. Among the millions of asteroids, a specific subset holds the key to the immediate future of space mining: near-Earth asteroids, or NEAs. These are asteroids whose orbits bring them within 1.3 astronomical units of the Sun, close enough to Earth to be considered accessible targets. NASA's Center for Near-Earth Object Studies, CNEOS, tracks over 30,000 known NEAs, with new ones discovered regularly. Not all are mineral-rich, but the sheer volume increases the odds of finding exceptionally valuable targets. Their relative proximity drastically reduces the energy and time required for missions, making them the prime focus for ambitious mining ventures and the subject of intense scrutiny from engineers and economists alike. Platinum group metals, or PGMs, represent a cornerstone of the asteroid mining business model. This group includes platinum, palladium, rhodium, ruthenium, iridium, and osmium, all characterized by their extreme rarity and unique catalytic properties. On Earth, these metals are found in concentrations of parts per billion. In certain M-type asteroids, however, scientists estimate concentrations could be significantly higher. For example, a single asteroid less than a kilometer in diameter could theoretically contain more platinum than all known terrestrial reserves combined, as highlighted by reports from the Keck Institute for Space Studies. This disparity makes PGMs an irresistible target for space prospectors. Beyond platinum, the quest for rare earth elements, or REEs, provides another powerful economic driver for asteroid mining. These 17 elements, from cerium to ytterbium, are not actually rare in Earth's crust but are rarely found in economically viable concentrations. They are critical components in almost every piece of modern technology: electric vehicle batteries, wind turbines, fiber optics, and advanced military systems. The geopolitical control over their extraction, primarily by China, creates significant supply chain risks for Western economies. Asteroid mining, therefore, presents a strategic opportunity to diversify sourcing and secure a stable, independent supply of these indispensable elements, mitigating terrestrial dependencies. While platinum and rare earths promise immense financial returns, many space economy advocates argue that water is, in fact, the most valuable resource an asteroid can offer. Water, found in significant quantities within C-type asteroids, is not just for life support, it's a critical feedstock for rocket propellant. Electrolysis can separate water into hydrogen and oxygen, the primary components of cryogenic rocket fuel. Establishing gas stations in orbit or on the Moon, fueled by asteroid water, would drastically reduce the cost of launching missions from Earth and enable sustained deep space exploration and colonization. According to orbital mechanics specialists, this could unlock an entirely new paradigm for space logistics. The concept of harvesting resources from space is not new. As early as the 1970s, physicist Gerard K. O'Neill envisioned colonies built from lunar and asteroid materials, proposing self-sustaining habitats in Earth orbit. His work, documented in The High Frontier, laid much of the theoretical groundwork for space industrialization. While O'Neill focused more on structural materials, his foundational ideas catalyzed a generation of scientists and engineers to look beyond Earth for resources. These early visions, often dismissed as fantastical, are now being revisited with renewed seriousness, as technological advancements bring O'Neill's high frontier closer to reality than ever before, shaping modern asteroid mining strategies. For decades, space exploration was primarily the domain of national governments. However, the dawn of the 21st century saw a seismic shift, with private enterprises stepping into what was once considered solely public endeavor. This commercialization of space has been fueled by decreasing launch costs and significant advancements in robotics and automation. Suddenly, the astronomical upfront investment required for asteroid mining seemed less insurmountable to venture capitalists. Companies, driven by the promise of unprecedented returns and leveraging innovative business models, began to emerge, signaling a new era where the pursuit of cosmic resources transitioned from government-led missions to a private sector gold rush. Among the first high-profile startups to capture the public imagination was Planetary Resources, founded in 2010. Backed by billionaires like Larry Page and James Cameron, the company's stated goal was to identify and eventually mine asteroids for water and precious metals. They developed Arcade series spacecraft for asteroid prospecting and flew demonstration missions to test technologies. However, despite significant early buzz and technological prototypes, Planetary Resources ultimately faced immense financial and technical hurdles. It was acquired by blockchain company Consensys in 2018, illustrating the profound challenges inherent in turning audacious space mining visions into sustainable commercial realities. Their journey, though ending in acquisition, validated the intense interest and potential. Close on the heels of Planetary Resources, Deep Space Industries, or DSI, emerged in 2013 with equally ambitious plans. DSI aimed to develop a full spectrum of asteroid mining technologies, from prospecting spacecraft like the Firefly to resource extraction and processing. Their focus was initially on water-rich asteroids, intending to produce propellant in space. They highlighted the economic viability of in-situ resource utilization, or ISRU, arguing that bringing resources back to Earth was less critical than using them to build a robust space economy. Like Planetary Resources, DSI eventually shifted its focus and was acquired by Bradford Space Incorporated in 2019, underscoring the formidable economic and technical barriers even for well-funded early entrants. While pioneering companies like Planetary Resources and Deep Space Industries encountered significant obstacles or pivoted, their foundational work was not in vain. They demonstrated the profound engineering challenges and the sheer scale of investment required, but also proved that the underlying scientific and technical principles of asteroid mining are sound. Today, the vision persists, fueled by ongoing research from space agencies and a new wave of startups learning from their predecessors. Companies like Astroforge are now attempting more focused approaches, often starting with smaller, more manageable goals. The narrative has shifted from grand, immediate returns to a more incremental, technologically sound path towards unlocking cosmic wealth. The journey to a near-Earth asteroid is an extraordinary feat of celestial mechanics and precision engineering. Unlike fixed orbits around planets, asteroids tumble and spin on complex trajectories, often requiring years of careful observation to predict their paths accurately. Once the target is selected, spacecraft must execute highly fuel-efficient, multi-year transfer orbits to achieve rendezvous. This involves intricate gravitational slingshots and precisely timed burns. According to aerospace engineers at MIT, navigating to and matching velocities with a small, irregularly shaped asteroid moving at tens of thousands of kilometers per hour is arguably more challenging than reaching a fixed destination like Mars, demanding groundbreaking autonomy and navigation systems. Upon successful rendezvous, the next critical engineering challenge is comprehensive characterization of the asteroid. Before any mining can occur, prospectors need to understand the asteroid's exact shape, spin rate, surface topography, internal structure, and critically, its mineralogical composition. This requires an array of sophisticated robotic probes equipped with spectrometers, LiDAR, radar, and mass spectrometers. Missions like NASA's OSIRIS-RX and JAXA's Hayabusa 2 have demonstrated this capability, meticulously mapping asteroid Bennu and Ryugu, respectively. As explained by scientists involved in these missions, this phase is akin to terrestrial geological surveying, but conducted remotely in a vacuum and microgravity, making it far more complex and data-intensive. Perhaps the most audacious engineering feat proposed for asteroid mining is not just extracting resources, but redirecting entire asteroids. The idea is to bring smaller, valuable asteroids into a more accessible orbit, such as one around the Moon or Earth, or even a parking orbit in cislunar space. Techniques under consideration include gravity tractors, where a spacecraft hovers near the asteroid, using its gravitational pull to subtly alter the asteroid's path over time. Another method involves robotic arms to directly nudge smaller objects. According to research from the B612 Foundation, even small changes applied over months or years can achieve significant orbital alterations, turning once distant targets into accessible quarries. While not directly for mining, NASA's Double Asteroid Redirection Test, or DART, mission provided an invaluable proof of concept for humanity's ability to intentionally alter an asteroid's trajectory. In September 2022, DART successfully impacted Dimorphos, a small moonlet of the asteroid Didymos, changing its orbital period by an astonishing 32 minutes. This kinetic impactor technique demonstrates that with sufficient energy and precision, we can modify asteroid paths. As reported by the Johns Hopkins Applied Physics Laboratory, which managed the mission, DART provided critical data on orbital mechanics and asteroid response, information directly applicable to future efforts aimed at redirecting asteroids for resource extraction rather than planetary defense, highlighting an important dual-use technology. With vast distances and significant time delays in communication, human-crewed asteroid mining missions are largely impractical for routine operations. This necessitates the development of highly autonomous robotics and artificial intelligence. These robotic systems must be capable of independent decision-making, adapting to unpredictable terrain, identifying and extracting resources, and performing maintenance without constant human oversight. Companies like Offworld are actively developing robotic fleets designed for these extreme environments, leveraging advanced machine learning for tasks like excavation and material sorting. The goal is to create entire self-sufficient mining outposts that can operate for extended periods, transmitting only critical data back to Earth, as outlined by roboticists in the field. For C-type asteroids rich in water and other volatiles, the extraction process is conceptually simpler than for metals, though still complex. The primary method involves enclosing a portion of the asteroid or capturing an entire small one, then heating it. Solar concentrators or microwave arrays can focus sunlight onto the asteroid's surface, causing the ice to sublimate into water vapor. This vapor is then collected and condensed into liquid water. This process, known as solar thermal processing, is particularly attractive because it relies on abundant solar energy and doesn't require heavy, complex chemical reagents. According to research from the Colorado School of Mines, this method offers a highly efficient path to generate vast quantities of water for propellants and life support. Mining metals like platinum and rare earth elements from M-type asteroids presents a different, more formidable set of engineering challenges. These industrial space alchemy processes must occur in microgravity and a vacuum, without the benefit of a stable gravity field or atmospheric pressure. Proposed methods include mechanical crushing and grinding to pulverize the asteroid material, followed by various refining techniques. These could involve magnetic separation, chemical leaching using benign reagents, or even vacuum distillation and smelting powered by concentrated solar energy. As metallurgical engineers point out, adapting terrestrial processes to the harsh space environment, while minimizing waste and maximizing efficiency, demands novel approaches in compact, robust machinery, a significant hurdle for nascent space industries. The absence of gravity profoundly impacts every aspect of material processing in space. Powders don't settle, liquids don't flow as expected, and gas bubbles behave differently. These microgravity conditions present both challenges and unique opportunities. For example, some processes like vacuum distillation are enhanced, as there's no atmospheric pressure to contend with. However, containing and manipulating powders or slurries requires entirely new engineering solutions, such as electrostatic fields or precise robotic manipulation. According to NASA's research into in situ resource utilization, or ISRU, understanding and mastering material behavior in microgravity is paramount for developing efficient orbital refineries and manufacturing facilities, enabling high-purity metal extraction and even novel material creation. Instead of bringing raw asteroid material back to Earth, a more efficient and economically viable approach involves establishing orbital refineries. These space-based factories would process extracted resources near the asteroid or in a convenient Earth-Moon L2 Lagrange point. This strategy minimizes the mass that needs to be transported to Earth, drastically reducing costs and energy expenditure. Processed water could be converted into propellant for use in space, while refined metals could be sent to terrestrial markets or used for construction in orbit. According to space logistics experts, these orbital refineries are not just processing centers, but also serve as potential hubs for space-based manufacturing, fueling an independent space economy and supporting lunar and Martian missions. The concept of in situ resource utilization, or ISRU, is central to the long-term viability of asteroid mining and space colonization. ISRU means living off the land, using local space resources to sustain missions and build infrastructure, rather than relying solely on expensive supplies launched from Earth. Water from asteroids, for instance, can not only become rocket fuel but also radiation shielding for habitats and oxygen for life support systems. Metals can be 3D printed into spare parts or used to construct large orbital structures. As emphasized by researchers at the European Space Agency, ISRU is the economic and practical linchpin for human expansion beyond Earth, transforming space from a destination into a self-sustaining frontier, rather than just a supply source for Earth. The promise of $1 trillion asteroid brings with it an unprecedented economic paradox. If a single asteroid delivered a colossal quantity of platinum, for example, far exceeding annual terrestrial production, the sudden influx could crash global commodity markets. Current platinum reserves are tightly controlled and valued for their scarcity. A massive new supply could devalue existing assets and destabilize industries reliant on stable pricing, potentially causing an economic shockwave. This scenario, often debated by commodity market analysts, highlights a fundamental tension. The very abundance that makes space mining appealing could, ironically, destroy the value it seeks to create if not managed carefully, complicating the investment calculus for space entrepreneurs. To mitigate the risk of market collapse, economists studying space resources propose various strategies for managing the influx of extraterrestrial materials. One approach is a gradual, controlled release of resources, slowly introducing asteroid-derived metals to the market to avoid price shocks. Another model suggests creating entirely new markets for these materials in space, leveraging them for in-space manufacturing rather than bringing them all to Earth. Professor Martin Elvis of the International Space University argues that the market for space-based resources could absorb vast quantities without impacting terrestrial prices, particularly water for propellant. The challenge lies in balancing immediate profit motives with long-term market stability and sustainable growth for a nascent space economy. Despite the market paradox, the potential for unprecedented wealth fuels the ambitions of space entrepreneurs. If an asteroid mining venture successfully identifies, extracts, and brings to market a significant volume of highly valuable resources, its founders and investors could become the world's first trillionaires. This isn't just about commodity prices, it's about pioneering an entirely new industry, establishing monopolies on off-world supplies, and controlling the future infrastructure of space. As venture capitalists like Peter Diamandis frequently emphasize, the returns could be exponential for those who solve the immense engineering and economic challenges. The race to be the first to tap into this cosmic wealth is a powerful driver for innovation, attracting audacious minds and immense capital, betting on a future where space truly makes fortunes. The journey to asteroid mining is paved with colossal upfront costs and inherent, long-term risks. Developing and deploying the necessary spacecraft, robotics, and processing infrastructure demands billions in investment before any return on capital can be realized. This translates to an incredibly long return on investment horizon, spanning decades rather than years. Venture capital firms specializing in deep tech and space ventures, along with government grants and strategic partnerships, are the primary funding sources. As financial analysts warn, this is not a short-term play but a patient, high-stakes bet on future technologies and markets that are still largely theoretical, requiring an appetite for risk matched only by the scale of the potential rewards. Beyond the engineering and economic hurdles, asteroid mining faces a complex legal frontier. The foundational document of space law is the 1967 Outer Space Treaty, or OST, signed by over 110 nations. It declares outer space, including celestial bodies, the province of all mankind and prohibits national appropriation. This common heritage principle raises profound questions about property rights for extracted resources. Does mining an asteroid constitute appropriation? International legal scholars remain divided. While the OST allows for the exploration and use of space, the line between use and ownership of resources remains ambiguously defined, creating a legal gray area that could spark future international disputes and hinder investment. In an attempt to provide legal certainty for its burgeoning private space industry, the United States passed the Commercial Space Launch Competitiveness Act in 2015. This landmark legislation explicitly grants U.S. citizens and entities the right to engage in the commercial exploration and recovery of space resources and to own, possess, use, dispose of, and sell those resources. It carefully avoids claiming sovereignty over celestial bodies themselves, focusing instead on the ownership of extracted materials. While lauded by U.S. space companies, international legal experts and other nations view this act with skepticism, arguing it could be a unilateral interpretation that conflicts with the spirit, if not the letter, of the Outer Space Treaty, potentially igniting a regulatory race for claims. The U.S. Space Act of 2015, followed by similar legislation in Luxembourg and the UAE, has not been universally embraced. Nations like Russia and Brazil have openly voiced concerns, arguing that such unilateral domestic laws undermine the principle of space as a common heritage for all humanity. They contend that any framework for resource appropriation should emerge from multilateral international agreements, not individual national legislation. This disagreement highlights a significant geopolitical fault line in the race for space resources. Without a universally accepted legal framework, the prospect of resource-rich asteroids could become a flashpoint for international conflict, rather than a shared opportunity, complicating global cooperation in space exploration and resource management. The fundamental question of who owns what in space remains largely unanswered by existing international law. If a private company extracts platinum from an asteroid, do they own it outright, or do they owe royalties to an international body? The UN Committee on the Peaceful Uses of Outer Space, or COPUOS, continues to grapple with these complex legal and ethical questions, seeking consensus on guidelines for resource extraction. As legal scholars at McGill University's Institute of Air and Space Law emphasize, without clear, internationally recognized property rights, investment in asteroid mining will remain hampered by regulatory uncertainty, potentially leading to resource grabs and legal battles, rather than orderly development of space's immense potential for all nations. The promise of asteroid mining also raises critical environmental considerations, though on a cosmic scale. One major concern is the proliferation of space debris. Mining operations, even highly automated ones, could generate fragments and waste, increasing the risk of collisions in Earth orbit and beyond. There's also the question of planetary protection, safeguarding the scientific integrity of untouched celestial bodies. Should all asteroids be fair game, or should some be preserved for scientific study? As space environmentalists argue, establishing responsible practices from the outset is crucial to avoid polluting the pristine space environment and preserve potential scientific discoveries, balancing resource exploitation with long-term ecological stewardship of the cosmos. Intriguingly, the technologies and capabilities being developed for asteroid mining often overlap with those for planetary defense. The ability to identify, track, and potentially redirect asteroids is crucial for both. A kinetic impactor, like DART, could deflect a hazardous asteroid, or with different parameters, redirect a resource-rich one. This dual-use nature presents an ethical and policy dilemma. Should mining companies be granted access to technologies that could also be weaponized or misused? As space policy experts at Secure World Foundation highlight, distinguishing between benign resource acquisition and potential harmful manipulation requires clear international guidelines and transparency, ensuring that capabilities designed for humanity's benefit are not repurposed for detrimental ends, balancing opportunity with responsibility. While private companies lead the commercial charge, national space agencies like NASA play a critical, foundational role in making asteroid mining possible. NASA's scientific missions, such as OSIRIS-RX, which successfully sampled asteroid Bennu, are invaluable. These missions characterize asteroid geology, test rendezvous and sample return technologies, and provide vital data on composition. NASA also invests in long-term technology maturation, funding research into advanced robotics, propulsion, and in-situ resource utilization. According to NASA's internal strategic documents, their role is to reduce the technical risk and lay the scientific groundwork, paving the way for commercial ventures without directly engaging in commercial mining itself, a public-private partnership essential for this new frontier. The European Space Agency, or ESA, is also a significant player in advancing asteroid knowledge and technology. ESA's Hera mission, slated for launch, will be Europe's contribution to planetary defense, following up on the DART mission's impact. However, Hera will also provide unprecedented insights into the internal structure and composition of asteroids, essential data for future mining efforts. Furthermore, ESA's Clean Space Initiative and ISRU research programs are directly applicable, developing sustainable space technologies and methodologies for using lunar and asteroid resources. As outlined by ESA officials, their approach emphasizes international cooperation and the development of sustainable, responsible practices for space resource utilization, complementing private sector initiatives with a focus on shared benefits. Japan Aerospace Exploration Agency, JAXA, has been a trailblazer in asteroid sample return missions, providing invaluable real-world data crucial for asteroid mining. The Hayabusa mission, launched in 2003, brought back microscopic samples from asteroid Itokawa, proving the feasibility of such endeavors. Its successor, Hayabusa 2, made an even more spectacular return in 2020, delivering pristine samples from C-type asteroid Ryugu. These samples have allowed scientists to analyze asteroid composition in terrestrial laboratories, validating remote sensing data and refining our understanding of resource distribution. As JAXA scientists confirm, these missions provide tangible proof that specific asteroid types contain water and organic materials, offering concrete evidence that bolsters the case for resource extraction and future space economy ventures. Despite the fervent rhetoric, most experts agree that industrial-scale asteroid mining is still decades away. Optimistic timelines often project initial returns within 10 to 20 years, but more realistic assessments push significant commercial operations into the 2040s or even 2050s. The sheer complexity of integrating advanced robotics, autonomous systems, propulsion, and processing infrastructure, all while ensuring economic viability, requires a sustained, multi-generational effort. As aerospace industry analysts frequently point out, the technological readiness levels for many crucial components are still relatively low. This isn't a quick gold rush, it's a long-term investment in a future where humanity systematically exploits the resources of our solar system, gradually building the necessary infrastructure piece by piece. The most pragmatic approach to initiating asteroid mining often suggests starting with the most immediately valuable and easiest to extract resource, water. Water-rich C-type asteroids are abundant and relatively easier to process compared to metallic ones. More importantly, the demand for water as rocket propellant and life support in space is immediate and critical for any sustained human presence beyond Earth. By establishing in-space gas stations with asteroid-derived water, costs for lunar and Martian missions can be drastically reduced, creating a self-sustaining cislunar economy. As space logistics strategists argue, focusing on water first allows the industry to mature technologies, build infrastructure, and generate early revenue before tackling the more challenging and market-disrupting metallic asteroid ventures. NASA's Lunar Gateway, a planned outpost orbiting the Moon, represents a critical piece of infrastructure that could directly support future asteroid mining operations. Positioned in a near-rectilinear halo orbit, Gateway will serve as a staging point for lunar surface missions and eventually, deep space exploration. It could also become a rendezvous point for redirected asteroids or a hub for processing facilities. With its ability to host astronauts and robotic systems, Gateway could serve as a forward operating base for managing asteroid missions, processing materials, and even storing resources before transport. According to NASA's Artemis program plans, the Gateway is designed as a foundational element, transforming cislunar space into an economically dynamic zone, directly leveraging asteroid resources for its long-term viability. Looking further into the future, asteroid mining is not just about bringing resources to Earth, it's fundamental to enabling human colonization of Mars and beyond. Martian settlers will need vast quantities of water for survival and propellant for return journeys. While Mars itself has water ice, supplementing it with easily accessible asteroid water could drastically accelerate settlement efforts. Additionally, structural metals from asteroids could be used to 3D print habitats, tools, and even spacecraft components directly in the Martian system or its vicinity. As proponents of a multi-planetary future, like SpaceX CEO Elon Musk, often articulate, asteroid resources are not optional, but essential for humanity to become a truly spacefaring civilization, ensuring self-sufficiency for off-world outposts. Beyond the initial fear of market crashes, successful asteroid mining could usher in an entirely new economic paradigm, an era of unprecedented resource abundance. Imagine a world where critical materials like platinum and rare earth elements are no longer scarce, but plentiful and affordable. This could catalyze new industries, drive down manufacturing costs for advanced technologies, and even foster global economic development by making essential resources accessible to more nations. As futurists suggest, the shift from scarcity to abundance could fundamentally alter geopolitics, reduce conflicts over terrestrial resources, and unlock entirely new possibilities for innovation, transforming Earth's economy and our relationship with material wealth in profound ways, if managed equitably. The vacuum and microgravity conditions of space offer unique opportunities for creating advanced materials that are difficult, if not impossible, to produce on Earth. Asteroid-derived metals could be processed into tailored alloys with superior strength-to-weight ratios or novel electrical properties. Microgravity can allow for the formation of perfect crystals or foams with unique structures, free from gravitational stresses. For example, some researchers are exploring ways to create high-purity semiconductors or superconductors in orbit. As materials scientists at the European Space Agency's Materials and Electrical Components Laboratory explain, these novel materials, combined with the abundance of extraterrestrial resources, could revolutionize everything from aerospace engineering to electronics, opening up entirely new frontiers in materials science and manufacturing. The successful development of asteroid mining will inevitably lead to the rise of its space industrial complex, a vast, interconnected network of industries spanning Earth and orbit. This complex will encompass everything from launch services and in-space manufacturing to orbital energy generation and resource processing. New supply chains will emerge, linking terrestrial demand with off-world supply. Think of companies specializing in space robotics, orbital maintenance, asteroid prospecting, or even space tourism fueled by abundant resources. As analysts from the Space Foundation predict, this burgeoning ecosystem will generate millions of jobs and trillions in economic activity, fundamentally altering the global economy and creating a new frontier for human enterprise and technological innovation. As asteroid mining operations become increasingly autonomous and interconnected, cybersecurity risks escalate dramatically. Fleets of remote robots, orbital processing plants, and command and control centers on Earth represent vast attack surfaces. A malicious actor gaining control of an asteroid mining mission could not only cause immense financial damage but also potentially endanger space assets or even create hazardous debris. The U.S. Space Force and various defense contractors are increasingly focused on protecting these vital assets from cyber threats, recognizing that the future of space resources hinges on robust digital security. Safeguarding these high-value, autonomous systems against sophisticated cyber espionage and sabotage is a paramount challenge for the nascent space economy. Powering large-scale asteroid mining operations will require immense and reliable energy sources. Solar power, collected by vast arrays, is a primary candidate for most operations in the inner solar system. However, for more energy-intensive processes like smelting or for missions further out, advanced nuclear power solutions, such as small modular reactors for space, are being explored. Energy will be needed for propulsion, autonomous robotics, heating for water extraction, and high-temperature metal refining. According to engineers designing these systems, efficient energy generation and storage are bottleneck technologies, requiring breakthroughs to enable sustained, industrial-scale operations far from Earth. This represents a significant engineering hurdle, integral to the overall economic viability and feasibility of asteroid mining. The rise of asteroid mining will necessitate an entirely new class of professionals, comprising a highly specialized and skilled workforce. We will need not just traditional aerospace engineers, but roboticists specializing in microgravity operations, space metallurgists, astrogeologists, autonomous systems programmers, and orbital mechanics experts. These roles will range from remote operators on Earth, managing fleets of robots, to potentially human specialists in orbit, overseeing complex processing plants. Universities and vocational programs are already beginning to adapt curricula to prepare for these future roles. As workforce development agencies predict, this emerging industry will create high-tech, high-paying jobs, driving educational innovation and attracting a new generation of talent eager to work on the high frontier of space. The notion of a space gold rush also brings forth significant ethical and societal questions. How will the public perceive private companies claiming and profiting from celestial bodies? Will there be concerns about resource exploitation by a select few, exacerbating global inequality? Environmental groups raise questions about astro-environmentalism and the long-term impact on the cosmos. Philosophically, some argue that space should remain pristine, a realm for exploration and scientific discovery, not industrialization. As ethicists and sociologists specializing in space issues point out, managing public perception and building a framework for equitable benefit sharing will be crucial for the social license and sustained growth of the asteroid mining industry, preventing a backlash against the commercialization of space. In an industry with such high barriers to entry and potential for astronomical returns, there's a significant risk of monopoly formation. The first entity or nation to successfully establish industrial-scale asteroid mining could gain an insurmountable advantage, controlling critical resources and setting global prices. This raises concerns about antitrust issues on a cosmic scale, potentially leading to a concentration of wealth and power in the hands of a few private corporations or powerful states. International bodies like the UN are keenly aware of this danger, seeking to develop frameworks that promote fair competition and prevent single entities from dominating access to space resources, ensuring a more distributed and equitable future, as international relations experts frequently warn. Central to the ethical framework of space exploration is the concept of planetary protection, the principle of preventing biological contamination of celestial bodies, both by Earth organisms and by potentially introducing extraterrestrial life back to Earth. For asteroid mining, this means ensuring that drilling and processing equipment doesn't inadvertently introduce Earth microbes to pristine asteroid environments, which could compromise future scientific study of indigenous life. Conversely, safeguards must be in place for sample returns to Earth. As established by the Committee on Space Research, or COSPER, these protocols are crucial. Balancing the drive for resources with the imperative to protect unstudied cosmic environments is a delicate but vital ethical consideration in the nascent asteroid mining industry. The economic and strategic potential of asteroid mining has inevitably ignited a new geopolitical race. Beyond the US and European nations, China and Russia are actively pursuing their own space resource strategies. China, with ambitious lunar and Martian exploration plans, views asteroid resources as vital for its long-term space dominance. Russia, while facing economic challenges, maintains significant space capabilities and a historical interest in space utilization. This competitive landscape could lead to a flags and claims scenario, where nations vie for perceived control over valuable asteroids, potentially exacerbating international tensions. As international relations strategists observe, the competition for extraterrestrial resources mirrors terrestrial historical patterns, albeit on a much grander, cosmic scale, driving innovation but also posing risks. Amidst the competitive race, there's also a strong argument for international cooperation in asteroid mining. Collaborative efforts could pool resources, share risks, and establish universally accepted legal and ethical frameworks, preventing conflict and ensuring equitable distribution of benefits. Organizations like the United Nations Office for Outer Space Affairs, or UNOOSA, actively promote international dialogue on space resource governance. Joint missions, shared infrastructure, and open access to data could foster a more peaceful and sustainable development of space. As space policy advocates argue, the scale of asteroid mining challenges is so immense that no single nation can truly go it alone, making cooperation not just an ideal, but a pragmatic necessity for long-term success and shared prosperity in space. While platinum group metals, rare earths, and water are the immediate focus, asteroids hold a far broader spectrum of valuable resources. Silicates, abundant in S-type asteroids, can be processed into building materials for space habitats, shielding, and even solar panels. Iron and nickel, plentiful in metallic asteroids, are fundamental for construction and manufacturing. There's even theoretical interest in helium-3, a potential fuel for future fusion reactors, found on the Moon and potentially in some asteroid types, though at lower concentrations. As future technologies evolve, the definition of a valuable resource in space will expand, revealing an ever-growing list of materials that could be extracted, processed, and utilized, feeding a fully self-sufficient space economy for generations to come. Ultimately, the race for the trillion-dollar asteroid is not just about terrestrial wealth or securing dwindling resources. It is a foundational step towards humanity's long-term vision of becoming a multiplanetary species. By unlocking the vast material and energy resources of the solar system, asteroid mining provides the means to build sustainable off-world colonies, to travel further and more efficiently, and to safeguard our species against existential risks on Earth. As space futurists envision, the ability to live off the land in space will be the key to permanent human presence on the Moon, Mars, and beyond, opening up an infinite frontier for exploration, settlement, and technological advancement, transcending our planetary cradle for good. The dream of the trillion-dollar asteroid, once confined to science fiction, is rapidly approaching the realm of possibility. The engineering challenges are immense, demanding breakthroughs in robotics, propulsion, and materials processing. The economic models are fraught with paradox, threatening to crash markets while simultaneously promising unimaginable wealth. The legal and ethical landscapes are complex, requiring global consensus on resource ownership and environmental stewardship. Yet, the relentless human drive for resources, innovation, and expansion ensures this pursuit is inevitable. The race is on, not just for a new source of wealth, but for the very future of our civilization, a future where humanity reaches out and embraces the boundless riches of the cosmos, forever changing life on Earth and beyond.